Hello everyone, my name is Xishun Liao, an assistant professor at University of Central Florida at its CEC department, affiliated with the NICE Digital Twin Initiative and Future City Initiative. I was previously a research scientist and postdoc at UCLA, and I got my PhD at UC Riverside. My research focuses on geospatial intelligence, human mobility, intelligent vehicle simulations, digital twins, and AI/ML technologies. We are building digital twin for smarter mobility, connecting the digital world of AI agents and AI networks with the physical world of human vehicles and transportation infrastructures. The research goal of my lab is to develop mobility digital twins that integrate multi-resolution modeling and simulation, capturing human mobility, behavior decision-making, and system-level optimization, sorry. And it's a multi-resolution, cross-domain, multimodal digital twins want to integrate as the figure shows here. And our societal goal is to create a safe, efficient, sustainable, and resilient mobility system that benefits society as a whole. In my mobility system development scope, it consists of two main elements, mobility AI agents and mobility AI networks. Mobility AI agents are the digital human beings and vehicles, and mobility AI networks are the digital transportation networks and its infrastructure. This framework allows us to autonomously generate that digital twin of a city. It's a network where it allows agents traverse and interact. AI agents need to make autonomous real-time decisions based on its environment conditions and develop the individual preference. AI agent can be very powerful, but definitely computational heavy and data hungry. So we need an AI network to provide system condition insights to overcome data and computational limits. For example, when we cannot simulate a mega city which contains, for example, in Los Angeles, there are 20 millions of population, we cannot simulate each agent. So we need an AI network. These two elements do not stand alone. They mutually influence each other. AI agents' behavior depends on the conditions of the AI network, while collective AI agents' behavior shapes the conditions of the network. This figure shows an overview of my research. For AI agents, I model driver and vehicles as which are the basic element in the traffic networks. Drivers has his own preference on like driving style based on their emotion and their personality. And modeling this driving behavior can predict their driver behavior. For example, car following, lane keeping, and decision making. At the same time, we build that vehicle digital twins allow us to do planning and control, do better coordination for safer, efficient traffic, combining with that driver behavior, driver digital twin, and provide personalized advisory for each drivers in our framework. So to support this, I built a digital twin simulation platform and field test platform to support that algorithm development and validations. I will introduce it in another video, but for this talk, I'm going to mainly introduce how do I build a resident digital twin by modeling the travel patterns and then use generative AI to generate the mobility data, like for example, trajectory traverse the city in a day, and hence we can integrate with the traffic networks, the road network road infrastructure to create a traffic digital twin. Hence, we can simulate the digital town to simulate a digital megacity. So how do we do that? Resonant digital twin we need to model the human mobility. First, we need to consider what kind of data we have. Right now, we have survey census data, transportation data like traffic flow, and GPS trace collect from different mobile device of all of the resident in the city, points of interest, and weather data, and even event calendar or even some traffic incident data. And then we want to use data to simulate what kind of people do what kind of activity, when, where, and how. How to get it means that travel by any type of travel mode. We need to consider that social demographic of these agents, these AI agents. We need to consider travel mode, the OD flow, their travel time, active time, interaction, and whether it's a recurrent activity or discretionary activity. And consider different factors about the activity developed or evolves over time, the change adapt to based on weather, holiday, large gathering events, or their social coordination with the household family or friends. We need to use a generative AI to create all this kind of trajectories, travel trajectory for the agent, for the citizen in the city to perform this full population simulation. This generative AI, this I would say generative AI's implication that generate the travel trajectory for each agents can be used in urban planning, mobility optimization, and public safety. For example, we know this person, if they are doing a lot of activity in certain area, we need to design the corresponding land use plan or make tax policy or make commercial planning for based on their activities. We also use the travel behavior to optimize their traffic flow, whether we need to evaluate whether we need to build new bridge or new road. We can test or simulate what's the reaction of those agents. Also for public safety, we can think about once we have GenAI to generate the background traffic stand for normal behavior, that would be very easy to identify those abnormally behavior. Also, consider we are in Orlando now, we can think about different tourist pattern, different travel behavior. Those will be a main part of our focus in the future. Those are more detail. I'll just talk about a little bit about this project. It's our first step, our foundation model, we call it deep active model. This research build scalable and transferable generative model for mobility trajectory synthesis. Let us consider the potential of a foundation model that can generate human activity pattern for an entire city. By inputting information about its individual, this model predicts that travel and active behavior of this type of person. Such a model can represent the next generation of traffic or travel demand, enable us to predict how our city operates in various scenarios. Previously, we have some active-based model, but they are very time-consuming to build, computationally expensive, and extremely difficult to transfer across region and culture. Once you need to build a model for another city, you need to spend millions of dollars or a couple of years. But this time, I propose this deep active model, which is data-driven, scalable, and easy to transfer. It generates 7 million of the chain in 3 hours. It transferred, and it's now, I'm going to show you later, it's now in test in 3 regions with the different culture and build very realistic data. Like in conclusion, this model's input will be the household social demographics, and the neural network in between would capture the activity and family features, family role features, capture the family influence of like father's activity may affect children's activity. Also capture temporal dependency between activities. For example, the first activity may have the sequential influence on the let's say the next 3 or 4 activities. And then the model can output will be some activity chain like homework, shopping, home, and it's their locations. Then we can use this activity chain with the locations to simulate the whole city. This is how we build it. To be very specific, on the left-hand side is the network design, social demographic information for the person and the rest of the household members, and their generated activity chain are concatenated in the time domain. A transformer-based network adopted to capture this interdependency between each input features. And the network can generate activity chain recursively. For example, this one from start of sentence, generate homework, and network generate the next activity, shopping again. And on the right hand side, these are the loss function. We need to put some regulation on their temporal order, their activity type prediction, and some allowance on time prediction sequential. So using this structure, the deep activity is a chain using that national household travel survey. I also design some evaluation metrics. Since we are not exactly want to predict one person, which is not very impossible, since our human behaviors are very random. So the system is evaluates using JSD to consider whether the distribution of the city of this type of people are correct, considering activity type, start time, end time, duration, and chain length, which means the number of activity. Also, activity realism evaluation for activity transition, completeness, and transition probability. It's compared with so many state-of-art neural networks, AIs, and even large language model to show that our foundation model, deep active model, can generate very good active pattern, considering comparing with others in terms of this evaluation metrics. So more detailed, more results. This algorithm is not a black box. Thanks to the attention mechanism, I can visualize the activity generation process from left-hand side figure shows how each family house member contribute to the step 1 to step 6 activity generation. For example, this is a weekday of an employee driver, 30-year-old male with 5 person in the household. The width of each line indicates the contribution of the factor to generate next activity. You can see looks like when he departs from home and the third child contributes a lot to his bi-meal activity. And also the third child contributes the most when they need to decide to go home from visiting a friend. You can see how a spoiled child behaves in the family. Moreover, this model is very transferable. You can see I test in Mexico City, Puget Sound near Seattle, and California, with different scale of region, different culture, with a very large active pattern deviation to show how transferable our model is with only using a very small local data set. Okay, so this is the result from location. We evaluate the location against real-world traffic data. Each activity was assigned with the location and load to a simulation. The results compare with the PAMS data provided by Caltrain CADOT and the traditional activity-based model called SCAG. You can see our proposed model can comparable to replace that SCAG, the origin model, which spent a few million dollars to build. And our results also align with the real-world traffic dataset very well. You can see the traffic volume and traffic speed on the selected or say representative highway from the California region. It's the LA, yeah, it's an LA region 405. It's very aligned, uh, lies well with the real traffic very well. And this part, yeah, I really like this video to show our demo. How do we generate a synthetic population of LA County of 20 millions of people? And we generate the activity chain for each agent. Each bubble means one each agent, and their activity from home, work, school, or buy meals along the day. And we assign these activities with locations and mode choice. Mode choice means like whether going to by bus, by train, or by car, or by walk. You can see that's how we simulate the whole population in Los Angeles County. If we zoom in, we can also see how each agents behave. For example, in UCLA campus, how this traffic congestion and shockwave are generated. And then this part is my favorite part. Previously, only do a macroscopic for megacity simulation, but when we consider the point of interest, for example, students would go to different school, high income people would go to maybe more expensive restaurant, and different people have different age or demographic may do different type of job. That at that time we need to assign location for each activities. My favorite part, okay, so this is a simulation for Westwood in Los Angeles. You can see real world POI implemented in this platform, which is open source as well. We can check agent in real time, we have their demographic, their activity sequence and locations on the right-hand side. Let's see how a UCLA student perform in a day. We can see the route planning stop, and we use a car in sumo to stand for the agent. We can see the student is leaving, departing from home to school and do school activity for a while. Now it's a parking lot performing school activities. And after maybe 30 seconds, which means stand for maybe 3 hours. But sometimes you see when we need to interference activity due to maybe some special events, like the route is closed, the student need to decide whether to still continue the activity. And then we need to modify the activity and let the agent to think. Since it's AI agents, we need to enable it for thinking activity. Now LLMs come to play to replace the next activity and decide a new location, new POI to execute. That's how that neural networks, AI networks condition would affect activities, AI agents, real-time decision. Okay, what's more important is that when we have events, let's say Taylor Swift come into play, is going to host a concert in your city. Definitely a lot of people would gather around to attend. Can we simulate this kind of thing? And for example, LA is going to have Olympics. How about football finals? Let's say the football finals happen at station D, and our simulation can select our attendance from the citizens and assign the activity, chain activity to show the event gallery. For example, without events showing on the left-hand side, which is normal traffic, normal daily life, but with the events, we can see a lot of people gather around near the stadium, where they're going to the restaurant or go to watch the game. Traffic is becoming more crowded. This is how we simulate the city dynamics under different scenario, different events. Okay, thanks for listening until here. I have presented the foundation model of our proposed research project, but there's still a lot of work undergoing and unsolved, a lot of questions. So, for example, I list some here. Uh, right now, we're using the survey data, the NHTS, the National Household Travel Survey, but for some region want to transfer to without that kind of survey data, what should we do? Survey data is also very biased. It depends on how we sample the residents. There are a lot of unseen, underrepresented population there. We didn't find them. Also, those data may be outdated. Our mobility pattern may shift over time. After the COVID, for example, our behavior have definitely changed a lot. Do we have detailed real world pattern like we collect the data from GPS devices, for example, our phone, our vehicles, and those data reflecting our real world, more realistic travel pattern? We have a lot of traffic events like incidents, like congestions. Can we reflect it and calibrate our model using the traffic data? We have different gatherings, large gathering like soccer game, football game, concert, to middle gathering like people going to cinema, and small gathering like group gathering, go a group of family, group of friends going to a park. Those gathering behavior can be reflected? We have hazard like hurricane in our Florida area. Can we do different simulation or different hazard, different scenario for different regions? How about real-time intervention? When we have this model, we have the background, normal behavior. If something happens, can we provide real-time intervention, real-time policy to decision maker? That require a lot of technology like multimodal, cross-domain data fusion. You can think about we have satellite data, we have image like street image, we have videos, we have like different type of survey, different types of GPS or point of interest data. Can we combine together with maintaining the privacy and trustworthy that not to avoid any not to violate any law? Another term is that geospatial and semantic data mining is also important. Think about there are so many information contained that state point and point of interest. For example, different people with different demographic may have different preference on POI. A high educated or high, um, like say, level of income people may have different job type or allocation. Rich people may go to more likely go to more expensive restaurant or supermarket. A large group of people may choose a restaurant with more space, while a single person possibly would go to a fast food, something like that. Large language models are also not a big chain. We do not. I show you a little bit, but we do not stop here. Can we identify the background meaning of the data using large language model? Can we use a better um, large language model to enable our AI agent to think, to enable our AI network to evolve themselves? For example, if there are lack of sensor, we're not sure what's happening in the no information, then can we inference what's going on using the surrounding networks or surrounding agents information? There's still a lot of work, a lot of information, a lot of possibility we can do for this type of job. So thank you for listening here. I truly welcome anyone want to join my team and wants to collaborate with me or with our very fascinating team. Please contact my email here, my website here. Oh, thank you all.